Good afternoon, everybody. I think we have the challenge to keep everybody awake after lunch. So that's, dear panelists, don't get too deep in the weeds there. So keep it exciting. My name is Marc from Keitz. As you probably know, I was ARPA-E. We are guided by really two questions. The one thing is our taglines for ARPA-E when we look at changing what's possible is really trying to push the limits of what we can do. But maybe more pertaining to the topics this afternoon is really when we try to decide if it's worthwhile investing into a particular area, the big question always is, if it works, does it matter? And so in that term, if it works, does it matter, is in the energy space really on two things. There's all the questions of what does it do to the CO2 footprint, what does it do to cost, but a really important part is also, can it be scaled? Because can it be scaled and can it be scaled fast? Because especially when you look at technologies that are relevant for climate implications, you want them to operate really, really quickly, or at least to be able to scale very quickly and come online very quickly. So the topic of this afternoon's panel is what to do with a solid carbon at scale. So that's in many ways very fitting. So on the one hand, looking at the different perspectives of what are the type of materials that we have, what can we do with that, but how also does it fit into the various application spaces, and some of which we may still have to create and invent. And so I think there's really a very exciting panel that we have this afternoon, and I just invite them in the order in which they are then going to give their presentations before we dive into the actual discussion. And let's start with Leonardo Spanu. He's a senior researcher for R&D and chemistry with Shell. Welcome, Leonardo. And then we have Carrie Masiello, and she's a professor here at Rice University of Earth, Environment, and Planetary Sciences. Welcome, Carrie. And then we have Adam Boies. He's a professor in the Division of Energy at University of Cambridge in the UK. And last but not least, Gianni Carfagni, professor of structural mechanics at the University of Parma in Italy. So with that, I would ask Leonardo to get us started.
Thank you. Right. So I'm going to present a few slides, and some of the topics actually were covered partially by Marc and other speakers, but I want to use this opportunity just to wrap a few things and stress some aspect of this challenge. Again, as Jay has mentioned, some cautionary note, you won't make any financial decision based on what I'm going to say in the next few minutes. So hydrogen at scale, what we do if we don't want to emit CO2. Well, currently we have three options, and Shell has been involved and is currently involved in all of the three. SMR plus CCS deployed in Canada, then we have water electrolysis and pyrolysis. So pyrolysis is particularly appealing for a company also that sells gas because require less energy to produce hydrogen compared, for instance, to electrolysis or to steam methane reforming. It's important to stress, actually, this one is not a competition between technologies. Most likely the future will need all technology options we could have to build a resilient portfolio. And based on the geography, based on your capital availability or social also acceptance, you will be able to deploy different of this option. But again, if we really believe in a hydrogen at scale, we cannot actually deny upfront any possibility. So pyrolysis, even someone with a degree in physics can understand, it's relatively simple on paper. You take a molecule that is simple and then you split into carbon and hydrogen, and possibly including renewable energy to provide heat to the reaction. On the hydrogen side, I believe the picture is relatively clear of what we can do with hydrogen. There are markets that are well established, and we know actually what are the drivers for the price. typically purity and pressure. Purity, for instance, may change depending on the application, and so is pressure. But what is carbon? So we keep seeing carbon, but actually carbon is an extremely complex zoo of morphology. So in these slides, and I'm going to spend a few minutes on these slides, I just want to summarize some of the current carbon markets. And I decided to summarize only carbon that you can buy on the market, and they are sold not for their calorific value, but for some form of functionality that is not just heat. So the first thing you notice is the sphere size. These are logarithmic plots, so the radius is just a logarithmic scale of the size of the market. And on the top, here on the top, there is the carbon equivalent. If we were converting all the production of hydrogen today, so 70 billion tons produced by pyrolysis, so it's about 210 million tons, which is matched more or less the size of the metallurgical coke or anodes for aluminum reduction. Unfortunately, those applications are very large in size, but at the end of the day, the carbon is used again to produce CO2. So there is already a market for carbon with some form of functionalization, but it's mostly used as a reducing agent for metals. The scale on the right, so we have all other forms of carbons that are typically used for their morphology, for their functionality. Even carbon black is 12 million tons, but still it's a small fraction of where we should go if we really want to deploy pyrolysis at scale. An important comment on carbon black is it comes with so many grades that cannot be seen just as a commodity. And this is an important message when we think about what to do with carbon. Even a large market is extremely fragmented, and the producer of carbon black, they have to work with the final user actually sometimes to tweak their formulation to make sure that actually fit the needs of the end user. So this is a key message when we start thinking about what to do with carbon. It's a very complex environment, and it's critical actually to work through the entire supply chain from the upstream to the end user. Another thing that's clear is the size of whatever carbon you use in a structural application is extremely small. So if we think about carbon fiber is 100,000 tons per year. So extremely small market compared to where we want to be. Can it grow? Sure, but we will discuss at the end of the seminar also what are the possible barriers. It's not just price or technology. There are other elements at the boundaries, and I think it will be the scope of the Carbon Hub also to really understand what are the constraints that may prevent any material actually to reach scale. It's not just cost, it's not just the process, but it's way more complex. So at the end, that's the initial question one has to pose it to himself. So there is this connection between the process and the product that you want to make. So far, if you want to use a pyrolytic route, you have to compromise on something. So you can only pick two, and so far there are no exceptions. If you want to really have this process at scale, well, at the moment we have to compromise. Because on one hand, there is the efficiency of the process. It could be energy efficiency, but also capital efficiency. So how well you employ the capital that you have spent. There is the morphology control, and then the purity. What does it mean? When I make carbon, I want to make in a specific morphology in such a way that can match the requirement from an end user. And to do so, most of the time I have to compromise either on the efficiency of the process or whatever impurity I'm including actually in my final product. This is key, even for application where on the surface relatively simple. So in a way that the landscape is split in two big regions. If I want to push conversion, so I want to create a process that makes as much hydrogen as possible with the least energy footprint, typically I end up with a lot of carbon, and controlling the morphology at this level tend to be extremely challenging. So there are, for instance, three possibilities for this carbon. I can do underground carbon storage, I can do soil remediation, or concrete additive. The other panelists will probably cover in more detail all these aspects. But a point I want to make is, even the simplest option, underground carbon storage, require a very careful control, for instance, of the impurity in my final morphology. So I don't want to leave in an underground storage something that is, for instance, detrimental for the environment. For soil, Professor Masiello probably will discuss the purity and the morphology play an even bigger role because eventually enter in the ecosystem. Same for concrete. On the lower end, we have what we call the advanced carbon morphology. So the ability to shape the carbon to drive performance. And it could be performance on the mechanical side for structural application or even in the electric side, for instance, for cables. Is it a new idea? No. Actually, if we look at the history of carbon nanotubes, one of the very first paper that was created from the 90s actually were using methane as a feedstock. So in principle, at lab scale, we know you can take methane and you can create nanotubes. But the key challenge here in the past, I would say 30 years, and there are two exceptions, we haven't seen really moving this property from the nanoscale to the macro scale. So, and that's a real challenge. So the material had potential at the nanoscale, but we could actually not be able to translate it into macro scale object that could be used. And for many reasons, mostly we were competing against a material that was already there, carbon black, with a very established supply chain. And at the end, nanotubes as an additive were not able to outperform carbon black. There are two exceptions, because around 2004, actually, Professor Window at Cambridge, who is in the audience, understood that we can actually start seeing this material in a different way, not as an additive, but actually a building block with something larger, like a fiber, a mat. And that's, in my view, a game changer. So carbon becomes not an additive, but become the main element of what has to be seen. So in view of time, so the idea is then we can possibly use this carbon to change the supply chain. For instance, this one is the supply chain for carbon fiber, what you could find in a wind blade or in a car. It's an extremely complex supply chain with many players, and possibly with pyrolysis effort we can skip at least half of it and go from a pyrolytic route to a carbon intermediate and into assembly phase. So it's not easy. There are different hurdles, and I think the main issue is we have to work across all the supply chain to improve a process that has been proven at the lab and really demonstrate that there is legs at the commercial scale, and actually this could be done in a viable way. I leave with a few more questions. For instance, specification will play a critical role. The product selection, it's a big issue. So are we replacing something or are we creating something completely new? So again, I want to stress supply chain. Probably there will be the need to rethink the full supply chain around this material. And last but not least, the footprint, the greenhouse footprint. If we truly believe this technology may have an impact in the way we produce hydrogen, we have to pay attention of the entire life cycle analysis and CO2 footprint of the product.
Carrie, next, and I think let's make sure that we change the slide.
Nope. Okay. I'm Carrie Masiello. I'm a professor in Earth, Environmental, and Planetary Sciences here. I'm also joint in the Biosciences Department and the Chemistry Department. I'm a biogeochemist, and that means that I have spent my career thinking about the fluxes of elements in the Earth system. So at a planetary scale. So I think about how carbon moves at a planetary scale between the atmosphere, the oceans, the soil, and the biosphere. I think about the sizes of reservoirs and the timescales of turnover of these reservoirs. And my particular area of expertise is understanding what controls the amount of carbon in the soil reservoir, the soil carbon reservoir, and what are the processes that make carbon stay in soil instead of being decomposed and returned to the atmosphere. Let's see if this works. All right. So, organic carbon in soil. This is my career. So, organic carbon is a really important part of soils, and it plays a number of just central roles. It's actually a relatively small component of soils by mass. So, between 0.5 and 5% by mass of soil is made up of organic carbon. But that organic carbon plays an outsized role in determining the performance of our soils, especially its performance in relation to plant growth. So, in a nutshell, the three things that soil organic carbon does: it provides nutrients, it holds on to nutrients in a plant available form. And so as it does this, it reduces fertilizer pollution and it increases the accessibility of nutrients for crops. It improves soil water properties. And so the two things that it does is it improves the ability of soils to hold on to water at a potential, at an energy state that's accessible to plants, as well as changing the ability of soils to drain. And those of you who live in Houston might know this. It used to be that T's Nursery had a back room, and in the back room of T's Nursery, you could buy charcoal. And if you asked the guy in T's Nursery what you were supposed to do with it, he would say, put it in your gumbo soil, it'll make it drain better. And so this is something that people have known for a long time, that aromatic forms of carbon can be helpful to soil productivity. And finally, it provides microhabitats for soil microbes. And this turns out to be incredibly interesting and incredibly complicated and very relevant, and finally, to the material that the Carbon Hub is proposing to produce. So we have a debt. The soil science community talks about it as a debt, but it's actually, another way you can think about it is a reservoir. So we have about 133 petagrams or gigatons, which is 10 to the 9th tons of carbon that's missing from our soils globally. And this carbon is missing because of poor agricultural practices, and the largely poor agricultural practices before the 1970s. So the reddest areas here are areas where we have the largest carbon debt, or you can flip it the other way around and you can think of it as these are the areas where we have the largest open reservoirs that can contain more soil carbon. And then this is a close-up of North America, where you can see the regions of North America where we have high carbon debts, high carbon reservoir sizes. So adding organic matter to soil is if you do it right, it can really improve the performance of your soil. And I want to start by being sure that we're all okay with the definition of organic carbon. So organic carbon, from a biogeochemist perspective, is any carbon that's not in the form of CO2, or I suppose diamonds are not organic carbon, but anything that's not in the form of CO2. And in soils, that means carbon that exists as plant biomass or fragments of dying microbial necromass, or little fragments of sugars, proteins, plant waxes, and charcoal. For scale, the way biogeochemists think about the Earth's carbon pools, we think in these units of gigatons, which is a 10 to the 9th tons. The amount of organic matter that we have in the Earth's soils is about 2,000 gigatons. That compares to about 830 gigatons of carbon that we have in the atmosphere currently as CO2. The pre-industrial CO2 value was about 520 gigatons. So we've accrued that difference. 830 minus 520 is what we have added to the atmosphere since approximately the Industrial Revolution. So not all forms of carbon that we add to soil provide the same benefits. And the key properties that I want to draw your attention to that are relevant to the material potentially produced by the Carbon Hub are particle size, the partial charge that the organic matter carries, which is incredibly important for maintaining soil fertility, and the ability of this material to potentially shuttle electrons between microbes that may be spatially separated from each other. So particle size is the most fundamental characteristic of all soils, and as you think about a soil additive, the most important thing, the first thing you want to ask is what the particle size is. And that's because particle size plays a central role in establishing how a soil drains. So sandy soils drain very well. They're terrible at holding on to water. You don't want to have a sandy soil in a dry environment. Clay soils hold on to water very well, but are terrible at infiltration. And so there's a sweet spot in the middle there, which is soils that are composed of, we imagine a triangle, of soils that have multiple grain sizes that allow for water to be held at a range of different potential energies. So here's a quick sort of graphical case of why you would care about the particle size of a material that you were amending to soil. If you have a sandy soil, you see a lot of movement down. You see a lot of leaching, so that's the soil on the left. For the soil on the right that's heavy in clay, you see a lot of overland flow. And for those of you who live in Houston, you live this experience. We have some of the heaviest clay soils on Earth. We live in an outlier in terms of soil properties in this city. And so we have very high overland flow in our soils. So the partial charges on the organic carbon hold on to nutrients. And this is incredibly important because more than 90% of soil's ability to hold on to nutrients is controlled by these partial charges. And the chemical composition, I wanted to just sort of provide you quickly with an approximate understanding of the chemistry of soil organic carbon. I want to draw your attention to the 10% of soil organic carbon that's already made up of charcoal. So 10% of the soil carbon on the planet already exists as aromatic forms. So how do we understand the potential for pyrolytic carbon from the carbon hub to be amended to soil? And so the closest analogy for this is something that we call biochar, which is charcoal that's intentionally made for amendment to soil. This is a plot of a meta-analysis. So we have enough data on the impacts of charcoal amendment to soil to understand its effects on crop fertility and to model it forward. And so the green numbers are positive impacts on crop performance and the red numbers are negative impacts. And so everywhere where you see red, you're seeing a negative impact on crop performance. Everywhere you see green, you're seeing as much as a 25% improvement in crop performance as a result of adding aromatic carbonaceous material to the soil. And so the challenges as we think about designing a material for soil amendment are, how do you make a material that really will improve soil performance? So not all biochar, which is a model that we have for this amended material, not all biochar does improve soil performance. The things we know we have to care about particle size, we have to care about the density of aromatic rings in each molecular unit. We need to create some structural defects so we get those partial charges to hold on to nutrients. And of course, we need collaboration with economists so that we can value the product. And then, as Leonardo said, it's extremely important that we understand the full life cycle. We have to get this product carbon negative. This is really important. We have to understand how to make this a carbon negative process. So how do you make a soil carbon sink? So burning fossil fuels right now is releasing about 10 gigatons of carbon to the atmosphere every year. As we think about pyrolyzing fossil fuels, we are reducing that source of carbon to the atmosphere. And that's great. We need to be reducing that source. But what we really want is we want to flip the direction of that arrow and make a carbon sink. And so there are a couple of ways we can do this. And this is fundamentally the essence of a nature-based solution, where I've changed the size of the fossil fuel vector here so that you can see it in context of the extremely large background fluxes from photosynthesis and respiration. So we're releasing about 10 gigatons per year from fossil fuel combustion. Respiration, plants' decomposition of organic matter, that's releasing more than 10 times that amount. But that's zeroed out by photosynthesis. So that's 120 gigatons of carbon that are going down from photosynthesis, matched by 120 that are coming up. So the net is 0. And I also want to point out that agriculture makes a number of other greenhouse gases, especially N2O and methane. So a nature-based solution fundamentally means, how do we drop that soil respiration rate? So if we have, instead of 120 minus 120, suppose we have 120 minus 110, we've just created a 10 gigaton carbon sink by eliminating that respiratory flux. And what if we can do something about those extra gases as well? And so one of the most hopeful things for me in thinking about aromatic materials in soil is early evidence that when we add charcoal, when we add these aromatic materials to soil, they trigger behavioral changes within the soil microbial community. And some of these behavioral changes we understand very well. So we understand that the presence of all of the aromatic functionalities in charcoal allows soil microbes to more efficiently denitrify and cleans up the emissions of a number of troublesome greenhouse gases that are already coming out from fertilizer use. This example here is a study that just came out for a 7-year field trial where they added 7 megagrams of biochar carbon per hectare, came back and found 14 megagrams of carbon had accumulated per hectare. And so this is the creation of an extra carbon sink. We call this a positive priming effect. And so getting at this mechanism of what's driving this kind of priming effect is how we can build a carbon negative nature-based solution with this material. And solving that problem is a highly multidisciplinary challenge. So it's going to require the collaboration of material scientists with microbiologists, with chemists and economists and social scientists. And I want to end by saying that Rice is a great place for this. We have all of these members of our community, and I think the Carbon Hub would be a great home for them.
Sure. Great. So thanks, Matteo, for having me come. When Matteo asked me to come speak today, he said, it'd be great to get the perspective of a young faculty member, kind of, and why they're willing to devote their kind of a significant portion of their career to this. And I thought, oh, well, only in academia is someone in their 40s considered young. So I thought, great, I chose the right profession. And then secondly, it is a bit of, has been a bit of a right turn for me. I'm in the energy department, or in the energy group within the engineering department at Cambridge. And really my kind of core science is aerosol science. So I study gas phase kind of nanomaterials. Largely that is carbon in another form, that's soot, that we're interested in why it's produced and how it's emitted. And of course, CO2 is, frankly, relatively easy to look at from combustion sources relative to soot formation. And about 10 years ago when I came to Cambridge, I had, in my grad school days, had played around with recipes of making carbon nanotubes as well. And it wasn't until I saw Alan's process that I became really kind of fascinated by this being something grander than just kind of a bit of a toy, and making something beyond that. So I'd like to talk a little bit about my perspective on it, which is really kind of an engineer's perspective on kind of the grand challenges, the hopes and challenges of scaled up nanomaterial production. So like everyone's shown kind of before here, there's an opportunity here to take natural gas and convert it into a solid form of carbon as well as fuel, and you give up about half the energy to do that. But that's the thermodynamic ideal. Do you give up half? In reality, we're giving up more than that right now. And so that needs to be dealt with, as well as the opportunity cost of not oxidizing that carbon into something else. So that's an economic opportunity cost. And both of those really ultimately depend on the quality of carbon that you're making as well as the process in which you're making it in. So we've been interested in that. One of kind of the basic questions is there any room here? So if you take a carbon nanotube process, which I've been interested in, or any carbon process where you're forming solid carbon and you're looking to displace some material, shown here on the upper right, is a line here where you look at values of the items that you're displacing somewhere in the economy, and you ask the question, well, if given that opportunity cost that I'm giving up, can I move into that market and still make a profit? And there is room there. I think there were numbers earlier where this kind of range here in the bottom was somewhere, I think maybe up to $200 per ton, but still there's room there for that to exist. But it depends on how good your carbon is, and therefore what you can displace in the economy somewhere. So the question is how good could it be? Well, the other reason to care about carbon and the quality of it is that there's kind of in classic life cycle analysis, I teach this course, that that when you have two products coming out of a process, the best way to value them and assign, say, CO2 emissions is based on their value. And so if you're producing coal, let's say, or something that has zero or maybe even negative economic cost somewhere in the future, or economic value somewhere in the future, all of the CO2 that you might be emitting gets assigned to the hydrogen, right? So if you make some CO2 in the process of making the carbon, and the hydrogen, all of that goes to the hydrogen. Now, conversely, if you're making diamonds, that have incredible value, of course, hydrogen you're getting for free. You would do it just to make the diamonds, right? And so, in reality, we're somewhere between those two. And we've recently done a bit of an kind of economic / techno-economic analysis of what ultimately where we would lie in a process where if we made solid carbon, ultimately what would be the CO2 emissions that would be associated with, given kind of current manufacturing processes. And so you see as the value of carbon goes up along the x-axis, you see the CO2 that's associated with the hydrogen goes down. And so you're displacing, what I'm not showing here is you're displacing a good somewhere like steel in the economy that has much higher CO2 emissions per unit mass than this as well. So it's kind of a net win. The higher you can get that carbon value, the better off you are. Now, how can we make carbon of value? Well, there's a variety of different ways. They've all been talked about today. We can do, one-dimensional carbon nanotubes, 2D graphene, or 3D carbon black. And we can start to look at structuring them not just on the nanoscale, but on the micro scale as well, in various kind of isotropic or aligned or composite structures. And then there's a scale even beyond that, kind of the more macro scale, still of just the carbon material alone, the solid carbon material. And then ultimately that carbon material is most likely going to be used in the form of some composite. So there's a large parameter space here that we've only just started to explore. We in the science community have really spent our time kind of on this first row here, and I would say we've spent relatively little time kind of farther down that, and that's the real opportunity for something like the Carbon Hub to explore more fully. So this is by far the most complex slide that I'll show, and my purpose in showing this is kind of no matter what the production process, independent of how you're making your CNTs, they've all started to converge. So here we're kind of mapping everything that we've found in literature in terms of, in this case, just strength, but we have analogous for thermal, electrical. And what you see is that as you densify along the x-axis here, you start to converge. And so the more dense you're able to make your carbon nanotubes in this case, the better the strength properties are. And it's irrespective of how you ultimately of how you made the materials. There are some qualifications within that, but largely the denser they are, the more the increased strength there will be. And I've put on here a few comparisons. So the best steel we're better than now, and the best carbon fiber we're just kind of right in the same ballpark as. So we're starting to get macro material properties that are now comparable to kind of the best materials. But again, we're not at scale yet. So let's talk about that scale. Well, first I'll just compare the other properties as well. So if we took, say, carbon nanotube materials, here are macro materials, relative to, say, copper or carbon fiber, where one would be that they're equal along the baseline here, you can see that by and large we're close in almost every regard. Electrical conductivity, we're still a ways off in terms of conductivity versus copper, but certainly much better than carbon fiber. And so across the board, these materials are starting to show at the macro scale properties that would be of interest for actual use. So the process that I've spent the most time looking at is a gas phase means where the nice thing is, as Leonardo showed, is that it's a single-step process. We put in precursors on the left-hand side, and you get out a macro material on the right-hand side. And I won't go into all the details of what we've learned of that over the years, but kind of the structure is one where we have nanotubes kind of at the nanoscale. They bundle and want to lower their surface area by van der Waals forces to form these networks of bundles we call an aerogel, and then ultimately scale up to form a mat or a fiber. And fundamentally, it's a really cheap process. So, about $1 per kilogram, or maybe even less. Now, the challenge is right now our reactor densities are low, and so the capital costs are what are high associated with this. And that's what we need to drive down by densification of the reaction itself. So, I'll show here some work that we've been doing with Tortec nanofibers, and this is their process. You can see the nanotube materials coming out. This is much higher densities than we get in our reactors at Cambridge, but the same fundamentals. And here, they're starting to show that you can do this kind of in real time, make fibers themselves. And NanoComp, do similar things with their materials. And I'm particularly interested in how can we get this density of the reaction increased so that these types of processes are even more economical. So we can do this at large scale, and really what you're seeing here on the left are not individual nanotubes, but these are bundles of nanotubes that have formed together to lower their surface energy. And it's really these, if we care about properties, it's understanding these bundles and that structure that is really kind of that next stage of investigation that we need to be doing. So my final slide on the process is one that was really actually Leonardo and Sander and others kind of pointed me onto some literature that compared catalysts just used more generally in industrial processes throughout the world, and that they have some kind of fundamental scaling laws that, like Matteo was talking about, that show whether or not they're economical. And so I thought, well, it'd be useful to plot what I know of carbon nanotube material production, not just from our process, but more broadly, relative to what industry thinks is required. So in each one of these cases, I'm showing with the lines here what the range of is that industrial processes that are driven by catalysis have to fall within. Relative to the carbon nanotube processes, the range of those that exist within literature. And in large part, we're doing pretty well. So, product costs versus catalyst costs were great. We're not using precious metals in this. The material production value is high. But where we really need to improve on are two areas. It's reactor yields, where only kind of the highest density reactors are just starting to eclipse what is needed, and catalyst selectivity. So we are still low in terms of our ability to have a catalyst produce a nanotube. In reality, we end up having lots of hangers-on in the process that don't ultimately grow nanotubes. And it's improving those two will ultimately drive down capital cost of this process and is really interesting science to boot. So with that, I'll just conclude by kind of saying that I think there are some real opportunities from this from both still kind of a fundamental perspective, but also real opportunities in terms of applying that knowledge to improve overall processes. And I'll leave it there. Thank you.
Gianni? Once again, just start talking.
Yeah. So I would like to thank Matteo and Marie for having invited me. It is a great honor. I teach structural mechanics and continuum mechanics, but I'm also a structural engineer. I do some consulting job. So I will bring you, I hope, the point of view of a structural engineer with respect to these new materials. And the first thing, I will start with a historic perspective. What has characterized the introduction of new materials in the construction industry? And in general, I would like to show you that it is the structure that shall adapt to the material and not vice versa. We have different types of structure, a truss, a frame, an arch, a cable, a dome, a membrane, and different construction materials. resin for masonry, timber, metals, and the last one is structural carbon. I would like to use this name, which means that it is a carbon-based material with structural capacity, because each material is characterized by different capacity in terms of strength, stiffness, weight, and so on, and it is the structure that has to optimize the capacity of the material itself. And to do so, start with this one. Until 300 years ago, the only construction material, the best construction material was masonry. This is a bridge designed by Leonardo da Vinci over the Golden Ore. It is an arch. You could only make an arch with masonry. And with the Industrial Revolution, you have the iron was made available. And this is one of the very first bridges made with iron in 1779. And it is an arch, but iron is much stronger than masonry. So if you have a slender element under compression, you may have a risk of buckling. So this is not the best way to exploit the material. So the great achievement is when you use iron as a suspension bridge. This is the Menai Strait Bridge. It is also mentioned in Alice, The Adventure of Alice in Wonderland, built by Thomas Telford. And as soon as you have a better material, you could also use cables. The Brooklyn Bridge is the most important piece of work of the 19th century. And it was built thanks to Emily Warren Roebling, which is considered the first woman engineer that has built this kind of big masterpiece, because her husband, Washington Roebling, was paralyzed, and his father-in-law, John Roebling, who was the one who introduced the cables in the United States, died just before the beginning of the construction. In the late 19th century, 20th century, in the 1950s, let us say, we have the introduction of prestressed concrete. And for these, the best structure is certainly a cable or a frame. But there has been engineers that try to use the prestressed concrete to build a cable-stay bridge. What is a cable-stay bridge? It's something like that, in which you have these cables which are inclined, they are suspended by a tower. This is built by Morandi, and unfortunately this bridge collapsed last year, killing almost 40 people, and now they are reconstructing that. It is in Genoa. I'm not not going the details for these slides, but I'd like to mention that there is an important problem for cable-stay bridge. When you try to pull an inclined cable like this, you have that the effect is to strain the material, but at the same time you have to recover the sag V. So your inclined cable with respect to its tensile stiffness appears much more compliant than the material itself. In the case of the Morandi Bridge, you can see that they are very inclined. So this type of effect, which was being studied by Ernst, is very important. So the cables are extremely compliant. And you can see that for 80 meters, which is the length on the horizontal projection of the length of the Polcevera viaduct, you have only 5% of the stiffness of the inclined cable. And indeed, there are many other problems with that during the casting of concrete. And in structural health monitoring for structure of this type is actually a very important issue. And from this point of view, I would like to mention that if you have an electric conductive structure, you can measure electric conductivity and you can correlate it with the structural properties. Then there are other problems correlated with the resonance of the cable at the stays. But what I like to mention that for an inclined cable, if you have a prestressed concrete, you can at least have a length L of the order of 50 meters. If you have a steel rope, high-strength steel rope, you have about 500 meters. If you use, for example, a CNT, carbon nanotube knit fiber, you have over the 5 kilometers, 10 kilometers that you can cover with a cable stay bridge. For example, this is the proposal by Riccardo Morandi for the Messina Strait crossing using a cable stay bridge. It is impossible to do that with steel, could be possible to do that with carbon nanotube fibers. If you have an hanging cable, this is a very, very simple exercise. You find out that there is a limit length. There is a limit length L of the hanging cable under its own weight, because beyond this length, the cable collapses because of its own weight. And this is given by a simple formula with some simplification. It is the ratio between sigma d, which represent the tensile strength, and gamma, which represent the weight per unit volume. And you find out that for iron, is it 1 kilometer? For strong steel, high-strength steel, is 5 kilometers. For glass fiber reinforced polymer, is 5 kilometers. For carbon fiber reinforced polymer, is of the order of 30 kilometers. For CNT knit fibers, it would be 150 kilometers. So if you have to construct something like that, which is the proposal, the final design for the Messina Strait Bridge with 3,000 meter main span, you find out that you are very close to the theoretical limit for steel, and this means that in this design, 70–80% of the capacity of a cable, of a supporting cable, is just used to support the self-weight of the cable itself. If you could use, for example, carbon nanotube knit fibers, you could think also making this kind of challenges, like the crossing of Gibraltar, 14 kilometers. The technique is very simple, the same used by Raebling patented for the construction of the Brooklyn Bridge. You just spin little wires, because the theoretical limit does not depend upon the area. And for example, I made a calculation that for the Messina Strait Bridge, you need 500,000 kilometers of wires to produce the fork-hanging cable that sustain the bridge. The two-dimensional counterpart of the cable is a membrane. This is a membrane structure for which you have to use many properties, and I don't have the time, but I can only tell you that all these kind of structural membranes are made by woven fabrics, and it would be nice to use carbon nanotube knit fibers to have this high performance, flexible textile, which could be used for many structural applications. So, what to use for structural carbon? What could be used for? We have the price. Of course, here are some prices that are common in Italy. They are very low for construction material. Nevertheless, there are structures that cannot be built with this kind of materials. I just gave you the example, cable stay bridge, a suspension bridge. There are many that are built nowadays. But you could also use to build shells made of panels made of structural carbon, or big plates that can be assembled. Another application is where the weight is important. This is the longest movable bridge in the world that is being designed over the Suez River, Suez Channel in Egypt. It's a 600-meter bridge, and if it was made with carbon and lighter, the movement, the deformation would be much less, and you could solve some structural changes. Or if you have a tall building, if you have a very slender structure, it means that the place that it is taken by the structure is less. You have more footage to cell. There are many applications. I just mentioned some that came to my mind. And my personal conclusion, of course, I'm giving you just my personal point of view, which is it's a very narrow perspective, but I can see great potential for structural carbon, because the strong points are essentially the lightweight, the high strength, the low creep, but also the electrical conductivity for structural monitoring. Of course, the weak points are small production, manufacturing, junction, and fire resistance. I can see that in short and medium terms, the application for cable and membrane structures using carbon nanotube fibers. Of course, there is a long way to do to have a practical application of this new material. There are many steps to be done. And last but not least, structural standards or guidelines which are necessary to render this material accessible to the engineering community. I thank you very much for your attention.
Thank you very much, and I would like to ask all the panelists to take a seat. Thank you, all of you, for really interesting presentations and also covering very diverse aspects. So I think we have a lot of ground to cover here, and I assume that there's quite a few questions there. So the one thing that just came to mind from my perspective is that we have sometimes a little bit more the aspect of production and then the aspect of uses. How do we articulate that what basically the targets are that we're shooting for? We heard a few times that there need to be some good targets with regard to what the materials require. Then the question is, can we make these materials? And then, but still, even further arching, do we really know all the properties that we want? So I think in the structural carbon, we have maybe some ideas based on old materials that we used and delineating things. With the carbon material, like the soil carbon, we have some ideas maybe as benchmarks with biochar, but do we need to push a little further along? So it's a little bit of an open question. How do you facilitate the conversation around what the targets are between the people that are making the materials versus the people that want to use the materials? And so I thought
the foams that you showed looked really interesting, just because of the very high porosity. That looked like it would have some really interesting soil applications.
Well, love to work with you on that. I mean, my thoughts on that are that the hype of carbon nanotubes is they can do everything, and therefore I think the worry is that they do nothing. And so embedded in your question is we do need to really find some early wins for the material kind of as it stands now. And I think tomorrow's event and events, we've done similar events at Cambridge, to really kind of say where are some natural wins for it now. I think where we're seeing emerging are thermal properties are really good. And it's a really good black body absorber. So EMI shielding, where you already have automotive and aerospace really wanting those properties, and that those aren't kind of on offer from the materials that they would typically use, might be some early wins. But then you would need to kind of take those and take that win and then use it to scale the process and then drive costs down, is where it would need to go.
Well, in order to use. Can you hear me? In order to use it as a structural material, it's not easy. There is a process that should be done. In Europe, in all Europe, you have a construction product regulation that regulates the use of any material, not only structural material in the construction industry. In order to have the possibility of using a new material, you need what is called an ETAC, which is some sort of European technical assessment that needs to be released by what is called the TAB, a technical assessment body. And you have to control, you are the producer, you have to assure what is the performance, what is the capacity of your material, and you have to say what you are going to do to control it. So you have to declare what are the properties, and you have to declare how you can check that these properties are maintained during the production. So when you buy these, you know what you are going to buy.
Anybody else that wants to chime in?
I think what I previously said, the key is actually to work across the full supply chain. I've seen so many times claims based on the enthusiasm, like maybe a researcher saying that will solve many problems. The end user doesn't even want to touch the material because standards are not there is no quality control in place, or even the replacement of existing supply chain is not working yet. So I think that the hope is that Carbon Hub will be the place to actually help this conversation across many players.
Yeah, thank you. So I think we have about 10 minutes, so I want to take the opportunity to open it up to the audience for asking questions. Are there any questions? I see one question over here.
Carrie, you showed that the net effect of charcoal or biochar really varied by location. It could be positive or negative, and I would hypothesize that the value of biochar or carbon is going to be very low, and we need millions or billions of tons stored, so it probably needs to be produced pretty locally. How well do we understand the reasons that drive those differences, and are there different ways that the materials could be produced that might be better suited for different soils?
Okay, so the differences, so you're talking about the plot of maize yield by geographic location. In general, you get the most significant improvement in crop performance in poor quality soils. So if you have a really excellent, so the one place where biochar is just giving consistently zero results is Iowa, because the soil is so good in Iowa. But in parts of Kenya and in the Sahel, results are showing doubling of crop productivity. But that's because crop productivity was very low. So this is with that particular carbonaceous soil amendment, the benefits are accruing in areas where agriculture is currently marginal. So creating, stabilizing some marginal agricultural areas. And there was a second half of your question.
Yeah. Do we need to design biochar in different ways for different regions?
Yes, it's going to be particle size. The particle size will be very important because they're going to be soils. You would not want to make Houston soils any richer in clay, but there are going to be places where a fine particle will be important in increasing the soil's ability to hold on to water.
Okay. Yeah, I think Dave and then...
Just to kind of put it in some type of scale, what particle size range are you talking about?
So sand particles go up to a millimeter, and clay particles are micron scale.
So something in the middle?
Yeah, well, spanning that range.
Okay.
Carl?
I want to add to that because I think it's not only particle size, right? But it is also things like the porosity of the particles, the surface areas of the particles, the charge, as you already mentioned, whether they are, anionic or cationically charged. So do you think that we have enough analytical tools available to somehow connect the analysis, the characterization of the various forms of carbon to their application and what they do in different kinds of soils? So as a more general topic, so the analysis of the various forms of carbon.
Yeah, so that's going to be a function of the ecosystem service that you want. So if you want an ecosystem service that has to do with carbon stability, so you want to stabilize carbon on the landscape, that's easy to quantify. So that's probably the easiest because all you have to do is measure total carbon content. If you want the ecosystem service of some altered soil water properties, that's also, again, 1960s technology. There are more complicated ecosystem services that people may be interested in delivering that become more challenging to measure. But the short answer is it's going to be a function of what services you're hoping for.
Thank you. So new structural materials tend to take a very long time to be put into wide-scale use. So carbon fibre is probably somewhere between 20 and 30 years from first thought to first commercial aircraft flying around. So if there was one thing you could do to speed acceptance of structural carbon, what would it be?
Well, I think that in order to use structural carbon, first of all, to really use for some real structure, you need to have a standardization, to decide to find out what are the properties, to assess the properties on a statistical basis, to find out what is the controls that you have to do, factory production control, to ensure that the mechanical properties are the same. You have to do some activity that takes into account what is, for example, the parameters that the engineer needs to perform a structural design, because these are all assessed on a statistical basis. For example, in Europe, for carbon fiber reinforced polymer, there is a technical group that is working to produce the Eurocode specific on this kind of structures. In Italy, there are recommendations from the Ministry of Public Works that covers all this kind of application that are very common for the restoration of historical buildings. Repaired using carbon fibers and carbon fibers reinforced polymers. So there is a lot of activity in that. I was talking about structural carbon, borrowing a term that is sometimes it is used, for example, structural glass, to characterize the structural use of glass that is material that has not been used for structural purpose very much. I like to use this because it is not a carbon fiber, it is not a carbon fiber polymer. I had in mind especially the carbon nanotube fibers. With Matteo, we did some work in the last year for the theoretical characterization of mechanical properties of that. And in my opinion, this kind of material are quite ready to be used for structural purposes. What is needed is this sort of technical assessment for their use in real civil engineering structure, including standards that the engineer can use, for example.
Okay, thank you. I think we have room for one more question.
Yeah, related to that question, what are the quick wins? You know, it seems like in some cases the process technology is coupled to the material properties that are being produced from a carbon fibers point of view, and in terms of soil carbon, that's been known for centuries, I would guess, in a certain sense. So where would you see the carbon hub playing, and then what would be the quick wins to show that we have these outlets for carbon in your respective fields?
I'm happy to take a second. So where we see kind of quick wins, or where they've, particularly when we've been working with the automotive and aerospace sector, or when they have a material that's being applied that's maybe not cost effective. So one example is working with an automotive supplier who makes housings for increasingly kind of electrified vehicles, so computer chips and cameras and all of that. They're using aluminum now as housings for many of that, not because of any structural application, but just because thermally aluminum problem using plastics. And so they're interested in switching those types of applications over to something like this. And I think kind of that goes to the question here is I don't think actually the early applications or the way into certain industries is probably not initially through structural. It's probably you get into automotive and aerospace via some other route, and it's serving some other function, and it happens to be structural as well. And then it gains acceptance, particularly in aerospace, where they're a very risk-adverse industry.
Any other additional comments on this?
I think one more something that's commodifiable is the reduction in non-CO2 greenhouse gases and the nitrogen oxides. So we do know that when we have this aromatic material in soil, microbes use it to dump their extra electrons, and you can have a microbe here and a microbe here, and if they've got this aromatic material that's connecting them, they can complete metabolic pathways that they might not otherwise be able to complete. And one of those that it looks like they're using carbon materials for is denitrification. And so that can remove the flux, that can greatly reduce the flux of N2O, which is a greenhouse gas that's about 300 times more powerful than CO2. And it also looks like it impacts the release of nitrogen oxides, so NOx from soils. And so in areas where we have agriculture abutting cities, it has the potential for impacting ozone production.
Okay. What's that?
May I add just one thing?
Yeah.
For civil engineering structure, it is a problem of scale, because with respect to automotive on the aeronautical application, the quantities that are needed are several orders of magnitude higher, and on the other hand, there is the problem that the technology is very poor with respect to the aerospace application, and consequently it is a use of this material in somehow, I would say, a mass way, because you need a huge amount of mass, and most of the time the people are using and manufacturing there, and not the skill and the ability of other people working in aerospace and automotive industry.
Well, thank you.